Hello everyone, our project is about classifying American Sign Language letters, and we are Bahjat Abugharbieh, Naren Reddy, Shreya Desai, and John Raj.
Did you know that nearly 10 million people are hard of hearing, or that 1 million people are functionally deaf? This is an insanely huge problem. In fact, statistics show that fewer than 1 in 20 people have hearing issues. Our group wanted to advance accessibility technologies for individuals with disabilities, so we use various machine learning algorithms which were taught in class to do image classification for sign language interpretation. We feel that the first step in the process for creating real-time sign language interpretation software is to create a software that can classify still images of sign language symbols made by hand into English letters. This was what our project focused on.
So for our project, we'll be using the ASL alphabet dataset that we got off of Kaggle and that can be accessed through the link on the slide. So the dataset is composed of a lot of things, but the parts that we'll be using are the 26 folders that contain 3,000 colored images that are 200 by 200 pixels corresponding to the letters in the English alphabet. Also, we'll be disregarding the letters J and Z as they involve movement, and therefore there might be different pictures for the different motions during the signing of such letters. This might negatively impact our classifiers and the accuracy of the classifiers. Therefore, we decided to disregard them in our project. The dataset also provides testing cases for the letters. However, we felt that they were quite limited. There were only one picture per letter. Therefore, we decided to split the training dataset into 80% training and 20% testing. Before we took the data into the training stage, we felt like a couple of modifications were necessary. First of all, the images were 200 by 200 pixels, and we felt that for some of the algorithms, this might be too much data to handle. For example, if every pixel was treated as a feature, then we would have 40,000 features. Therefore, we used Python to simplify the images to 64 by 64 pixels. We also converted them from colored images into grayscale, and you can see a sample transformation on the slide. And also, out of every set of 3,000 images per letter, we picked 1,000 randomly chosen images so that we could also reduce the number of inputs. And as we mentioned before, this 1,000 images will be split into 80% training and 20% testing. Even though in the previous slide we reduced the size of the images to be 64 by 64 pixels, this would still leave us with 4,096 features, which we believe would still be computationally exhausting to train the supervised learning algorithms. Therefore, we decided to apply PCA to reduce the number of features without significantly impacting the performance of the model. From the PCA model, we discovered that the first 400 principal components capture more than 96% of the total information or the total variance in the model. And therefore, we'll be trying out and testing this PCA modified dataset for the SVM and random forest algorithms and seeing how it compares with the original dataset. So the classification algorithms that we'll be using in our project are support vector machines, decision trees and random forests, and convolutional neural networks, CNN.
Support vector machines are a supervised learning method that is used for classification, regression, and outlier detection. This machine learning method is used to find a hyperplane in a multidimensional place that classifies data points into different classes. There are 26 letters in the alphabet, but we excluded the letters J and Z in our analysis because those two letters involve movement. We are looking at 24 letters. We'll be using this algorithm to find the optimal decision boundary that splits our 24 classes. We initially use SVM with a linear kernel and regular dataset to do image classification. We found that the accuracy of that particular model to be 0.7585. We then use SVM with a linear kernel and a PCA modified dataset to test the new accuracy and compare the results. And we increased the accuracy by 0.046 and got an accuracy of 0.805. The PCA modified dataset helped us increase the accuracy of the SVM model, and we decided to use the PCA modified dataset for the rest of the SVM analysis. We use cross-validation to find the most optimal values for parameters that would yield the most accurate results. We found the model values for C, degree, gamma, and kernel. C determines the trade-off between maximizing the margin and error minimization. Kernel determines whether the decision boundaries are linear or nonlinear. Degree and gamma impact the model only if the kernel is nonlinear. Our optimal values are C equals 1, degree equals 3, kernel equals linear, and we get a model accuracy of 0.805, which is about 0.81. Looking at the results, the model performs differently when it classifies various letters. Our SVM model classified some letters better than other letters. For example, the letter N is able to be classified accurately 100% of the time, while the letter B is only classified accurately 58% of the time. Other letters that the SVM did well in classifying accurately are C, F, I, L, P, Q, and T, because they were letters that were classified accurately 90% of the time or greater. Some letters that were not classified as accurately as we would have liked were B, D, G, M, U, V, and Y, that were only classified correctly between 50 to 75% of the time. We can also see that some of the letters, such as the letter L, had a very high score for precision, recall, and the F1 score. But other letters, such as the letter B, had a very poor results in all these categories. Overall, the accuracy of the model is 0.805, which is around 0.81, but we will look at other machine learning methods to get a better and more accurate model.
Decision trees are a family of classifiers that interprets each feature separately and splits the data based on its values. In our case, a decision tree will split the data based on the pixels as a value of their intensity. In other words, the tree will start at 1 pixel and split the data into 2 branches, the first if the intensity is high and the other if the intensity is low. It will recursively repeat this process until we get to the leaves of the tree, or we decide to stop at a certain level to avoid overfitting. Our optimal decision tree obtained an accuracy of 0.8. However, instead of trying to figure out how we can improve this model, we decided to use ensemble learning, which we'll talk about in the next slide, as well as random forests to try to achieve a better accuracy. One way to improve the accuracy of the classifiers is to use ensemble learning. In this case, we'll be using bagging, where multiple decision trees will be trained and the output will be a combination of the results from the decision trees. Also, instead of manually training multiple decision trees, we will be using the random forest algorithm, which not only trains multiple decision trees, but also introduces an extra element of randomness by training each subtree on a specific subset of features. Moreover, we will be tuning our model's hyperparameters using three-fold cross-validation. Specifically, the parameters that we will be optimizing are the number of decision trees, the maximum depth of every decision tree, the minimum number of samples required to split a node, and the maximum number of features to consider when splitting. First of all, we started by testing the model with both the original dataset and the PCA modified dataset. Even though we predicted that the PCA modified dataset should give better results, it turns out that on our dataset, the original features performed better. And the best performing model, which was trained on the original dataset, had the following results. So first of all, from the cross-validation, we can see that the optimal hyperparameters were maximum depth of 15, maximum features of 150, and number of estimators, which are the number of decision trees, were 800, and the minimum samples to split a node were 5. And the results of the model also can be seen from these two plots. From the bar plot, we can see the total percentage of correct predictions for each letter. And as we can see, it is not an equal split. It actually performs very good for the majority of the letters, but performs horribly at only some of the letters, like D, X, and T. And if we disregard actually only these 3 letters, then we see that the accuracy of the model jumps to 96%. But overall, it has an accuracy of 90%. Here we try to understand why the original dataset performed much better than the PCA modified one, and why some of the letters are getting misclassified for others, even though if we look closely in the confusion matrix, we can see that the letters that are being misclassified do not have clear similarities between them. And we believe that it was due to the nature of decision trees in random forests and how they work, as they are unable to capture spatial connections well. Also, after inspecting the individual principal components, we could see that the changing backgrounds had a negative impact on our model. On the other hand, our model still achieved an overall prediction accuracy of approximately 0.9, which is overall pretty good.
The final classification model we utilized were convolutional neural networks. CNNs are a deep learning algorithm that is specifically designed to process pixel data. The algorithm consists of an input layer, multiple hidden layers, and an output layer. These hidden layers include convolutional layers and pooling layers. When we incorporate these stacked layers, the network is able to learn higher level features. This enables CNNs to require much less preprocessing and perform at much higher levels than other classification algorithms. Interestingly, the foundation of the networks mimic the visual cortex of the human brain, which allows the algorithm to break down the images. In our model, we incorporated 3 different architectures of the convolutional neural networks: AlexNet, LNet, and an architecture that we put together using various sources. The final architecture that was utilized to provide us with the highest accuracy was put together by implementing a combination of the general architectures. This model inherits layers and hyperparameters from AlexNet and VGG16, both architectures that use max pooling layers. For each architecture, we adjust the hyperparameters to maximize the accuracy. Once we decided on our final architecture, we found that the hyperparameters which had a large impact on model efficiency and accuracy were batch size and number of epochs. We also found that adjusting the size of the validation set had large implications on the testing accuracy. The batch size defines the total instances of training data that will be propagated through the network in one iteration of the algorithm. There are advantages and disadvantages associated with both large batch sizes as well as small batch sizes. The advantages of using a small batch size is that it generally requires less memory, and therefore it typically trains faster. The disadvantage of using a small batch size is that it lessens the accuracy of the gradient computation, which leads to less accuracy overall. In order to combat this, we fitted the model using a small batch size and then performed 3 more subsequent iterations, each with a larger batch size, in order to create a model that was both efficient and accurate. Another hyperparameter which we adjusted was the total number of epochs. The number of epochs indicates the number of passes for the whole training dataset that the algorithm will complete before stopping. The accepted method of deciding this number is to run an arbitrarily large number of epochs and observe when the accuracy of the validation set starts to settle. Once this accuracy settles, any more epochs will potentially overfit the data. Finally, after adjusting the size of the validation set, we found that the optimal split was 90-10, 90% training and 10% validation. Other less optimal splits we tested were 50-50, 70-30, and 80-20. Typically, for very large datasets like ours, smaller validation sets lead to better performance. After fitting each architecture, we reached the highest accuracy with our own model at just below 94%. As seen in this heat map, the letters H, R, S, T, W, and X are misclassified the most. You can see in the accuracy and loss evolutions that we've reached a happy medium between underfitting and overfitting. As we can see, the validation accuracy and loss begin to settle and plateau. Any fewer iterations and the model could potentially underfit the data. Any more, and the model would likely overfit the data.
As you can see, the convolutional neural network worked the best with a final accuracy of 0.9375, followed by the random forest, and lastly the support vector machine. This makes sense in relation to our project because CNN typically does work best for image recognition due to its hierarchical model that builds an extensive network. In the future, there can be several ways to strengthen the research done in this project. We can incorporate a live translation of ASL signs into English letters and develop an RNN or CNN that can handle video data to include words and sentences. We can also implement more established CNN architectures like VGG16 and exception to allow for more computational power and possibly raise the accuracy even more. Lastly, we can utilize nonlinear dimensionality reduction techniques instead of the PCA to visualize the data better and improve performance. The possibilities for such a project are endless. These machine learning algorithms allow us to move towards filling in the gap for the deaf and hard of hearing, and there are numerous ways to incorporate our findings in order to proceed to have smooth interactions between and with those who are hearing impaired. Thank you for your time.